Our team was tasked with designing an emergency scissor jack. Given a basic design, we had to find the dimensions of all the components, the materials to build it with, and the overall weight of the assembly. The basic requirements for the jack were as followed. It needed to lift 17,000 newtons, have a maximum height of 51 centimeters, and also have a safety factor of 2.25. With doing all this, it had to be operated by a single adult. The strategy we decided to use for the project was to first create a CAD assembly. Each piece was created with initial estimated dimensions. Once we had designed it so that maximum height would be met, we would then find the stresses in each component and readjust the materials and dimensions until the safety factor had been met for each part. One of the first tasks that we took was to create a simple design that was still effective. We began with sketching every part out to get a general idea of how everything should look. We assumed the rough measurements of the length, width, and height of each part and later calculated them with proper equations. After getting a generalized idea, we sought after a CAD software to build the model for our custom jack. At this point, we did not realize our final design was going to differ so much from our original schematic. Each part was created in a program called OnShape based off of our own design and calculations. Before we began our calculations, we assembled the parts and could see that they were not proportional and some needed to be recreated. We began to recreate certain parts and gave new dimensions to work with the model and began to work all the calculations on paper to get exact dimensions. Within the week of our first calculations, we realized our holes needed to be bigger than originally intended, our screw was way too short, and our thickness of the parts were all too thin. It took a while, but we were able to find the correct materials and dimensions to make our jack perform as intended while also being safe. We created a simple drawing of our jack for us to reference while we performed calculations. The parts were assembled and we labeled the arms so that calculations were not mixed up in between them.
A free body diagram for the top bracket to solve for the forces in the top arm, labeled 1 and 2. The equations of the equilibrium state that the sum of the forces in the y direction must be equal to 0. Since the loading is symmetrical, we can set F1 equal to F2. The maximum force will occur when the jack is fully lowered, and we found that the angle between the arms and horizontal axis is 7.4 degrees at that point. Solving showed that the top arms were under 66 kilonewtons of compression. We then did the same with the foot, setting the sum of the forces equal to 0, and then using symmetry to simplify the equation and solve for the forces in the bottom arms. We found this also to be 66 kilonewtons in compression. Using the joint on the left side of the assembly, we then solved for the tensile force in the power screw, which was found to be under 131 kilonewtons of tension. We found that the weakest point of each of the arms was at the pin-loaded holes. So we decided to use these to find the thickness needed in the arms to make them safe, using the 15 millimeter diameter and the 40 millimeter width of that section. We found a D to B ratio of 0.375. Using that and the stress concentration factor graph for a pin-loaded hole, we found that the stress concentration is 2.9. The nominal stress in a pin-loaded central hole is given as the force in the member over the difference in the width and the diameter times the thickness of the section. The maximum stress is the product of the nominal stress and the stress concentration factor, which can be solved for the nominal stress. Setting these equations equal to each other gives us the last equation. The maximum stress can be found by dividing the yielding stress of the metal, which we decided to use as ASI 4340 normalized steel by the safety factor. This gave us a value of 383 megapascals. Plugging in all of the variables and then solving for H gave us a thickness of 10 millimeters for the arms. Now that we have the dimensions for the top arm, we can assume that the bottom arms will require the same thickness, width, and pinhole diameter. We then adjusted the lower arms and top bracket to fit the upper arm, and the foot was adjusted to fit the lower arm.
So for power screw, we started with figuring out the minor diameter. I was then able to find the major diameter by looking at table 10.2 on page 414 in our book, which was 27 millimeters, and the minor diameter found in our calculations earlier was around 23.33 millimeter. The pitch was found from the same chart as well on page 414, which was 3 millimeters per thread. The lead was found by multiplying 1 times the pitch, which was also 3 millimeters. The threaded depth was found by using the formula 0.5 multiplied with pitch, which gave us 1.5 millimeter for threaded depth. On top, which is mean diameter of the thread dm equals to major diameter d subtracted by pitch divided by 2. After I found the mean diameter, which was 25.5 millimeters, I plugged that into the lead angle formula, which is the formula on the bottom, which is tan lambda equals lead over pi times dm, and I was able to find the lead angle, which was 2.14 degrees. We then focused on the torque required to raise the load, and for that we needed to find all key components to be able to plug in. A friction coefficient F of 0.12 is used to determine the raising torque, and coefficient of friction of collar washer FC is assumed to be 0.009, and alpha N was calculated to be 14.5 degrees, which was converted to 0.253 radians. And all the other variables such as dm and lead was calculated prior torque equation. After plugging it all in, we found torque needed to raise the load to be 216.99 Newton meters. Force an average person could exert was found next. Taking into consideration the weight of an average person using the car jack is 130 lbs or 58.97 kilograms, and assuming one can lift at least half of their body mass, which is 29.49 kilograms, we use the formula for force, which equals mass times acceleration, plugging in the mass 29.49 kilograms and multiplying it with the acceleration of gravity 9.81 meters per second square, and we find the force average person exerts to be 289.3 newtons. After I found the torque required to lift the load in the last slide, which was 217 Newton meters, we were able to plug in the values of the torque and force and were able to find out the length of the handle, which was 0.75 meters. Since we now have dimensions for all of the components, we need to find the safety factor for each of the components to make sure they meet or exceed the safety factor given. For the top bracket, the weakest points are at the pin-loaded holes. This bracket is made with AISI 4140 normalized steel, so it has a tensile yield strength of 861.8 megapascal. To find the maximum stress in the pin-loaded holes, we have to multiply the nominal stress by the stress concentration factor. The nominal stress is calculated using half of the force in the component, as it is divided between the two sides of the bracket. This gives us nominal stress of 54.1 megapascal. We then find the stress concentration factor using the stress concentration factor graph and the ratio of the diameter of the holes to the width of the section. Using the ratio of 0.2, we find the stress concentration factor to be 5.5. Multiplying this by the nominal stress gives us a maximum tensile stress of 297.6 megapascal. The calculated safety factor was then found by dividing the yield strength by the maximum tensile stress, which was found to be 2.9. Since this value exceeds the given safety factor, the pin-loaded holes will not fail.
Since the bottom bracket's dimensions for the pin-loaded hole are the same as the top brackets, and they are the same material, we can assume that the pin-loaded holes in the bottom are under the same stress and will have the same safety factor. Therefore, the bottom bracket is safe. We then needed to find the safety factor of the power screw, which was under tensile and torsional stress. The plan is to create a Mohr circle to find the maximum stresses and then use the yielding strength to find the safety factors for torsion and tensile stress. The tensile yielding strength of AISI 4140 normalized steel is 861.8 megapascals. Multiplying this by 0.58 gives us the shear yielding strength, which is 500 megapascals. The normal stress in the x direction is found by dividing the tensile stress by the cross-sectional area of the screw. This gives us a normal stress of 307.5 megapascals. We then find the polar moment of inertia, which is given by the equation pi times the diameter to the fourth power divided by 32. This gives us a value of 2.9 times 10 to the negative 8 meters to the fourth. We use this value along with the torque and radius of the cross-section to find the shear stress in the XY plane. This is found to be 87.5 megapascals. Now that we have the stresses, we can begin to build our Mohr circle. The equation for the location of the center of the circle is the average of sigma x and sigma y. Since the stress in the y direction is equal to 0, we can ignore it. This gives us a center coordinate of 153.75 megapascals on the x-axis. We then find the radius, which is equal to the maximum shear stress, by taking the square root of the average of the normal stresses plus the shear stress in the xy plane squared. This gives us a maximum shear stress of 176.9 megapascals. Using the center and the radius of the circle, we create the Mohr circle shown here. From the circle, you can see that the maximum tensile stress is 330.7 megapascals. We then calculated the tensile safety factor as the quotient of the tensile yield stress and the maximum tensile stress. We found this to be 2.6. We then did the shear safety factor as the quotient of the shear yielding strength and the maximum shear stress. We found this to be 2.8. Since these both exceed the given safety factor, the power screw is safe. Once we found that all of the components were safe and had the final dimensions, we calculated the volume using a CAD software. We then multiplied that by the density to get the mass of the jack, and then multiplied that by the acceleration of gravity to find that the weight was 217 newtons. With all of our calculations performed, we feel confident that our design meets and exceeds the requirements. We experienced constant reworking and re-engineering based off of different materials before we got every part to perform as expected.